Hello students, welcome to the lecture series of rotational dynamics. In this series, the topic that we are going to study today is angular momentum, also called as moment of linear momentum. It is a quantity in rotational dynamics which is similar to linear momentum. So in linear motion, we have linear momentum represented by vector p bar. In the similar manner, we have angular momentum in rotational dynamics represented by vector L bar. Today, we'll start by defining the angular momentum for a point particle. To see that, let's consider a coordinate system. So I have drawn a coordinate system on the screen. So I have x-axis, y-axis, and a z-axis coming outwards. Now, with respect to this coordinate system's origin, I place a particle whose position vector with respect to origin is r bar. And the particle is said to have a momentum represented by vector p bar. Now, if I want to find out the angular momentum, of the particle about origin, then it is written as LO bar, represented as LO bar, and the formula for that is R bar cross P bar, where R bar is nothing but the position vector of the particle with respect to origin, and P bar is nothing but the momentum vector of the particle. So angular momentum is nothing but the cross product between position vector and momentum vector. So this is the formula. Now, if I want to find out the magnitude, it will simply be Rp sine theta, where theta is nothing but angle between R bar and P bar. R bar and P bar. So for that, I just extend this direction of R bar, and this will become then the angle between R bar and P bar, which is nothing but theta. So this was the definition for angular momentum of a particle about a certain fixed point. But what we are going to see today in this lecture is the derivation for the formula for calculating angular momentum of a rigid rotating body. Okay, so let's start with the derivation for the formula for angular momentum of a rigid rotating body. So for that, on the left hand side of the screen, I have considered a rigid rotating body, and I have pointed out some masses, point masses on the rigid rotating body. So we have mass m1, mass m2, and mass mn, and the distances of those masses from the axis of rotation of the rigid body are nothing but r1, r2, and so on up to rn respectively. So for any ith particle, we can see that the radius vector of the particle with respect to the axis of rotation and the tangential velocity, that is v, they all are perpendicular. The r's and the v's all are perpendicular for all the particles. So we can write down that the tangential velocity vi is nothing but ri into omega, and the linear momentum for the ith particle can be written as mi into vi. Therefore, for each particle, by using the definition of angular momentum, L bar is equal to R bar cross P bar. So for ith particle, we can write down Li bar is equal to Ri bar cross Pi bar. And by substituting in the place of Ri bar, Mi and Vi, I can write it down as Ri bar cross Mi into Vi bar. Now Mi is a scalar. I take it out of the cross product, and what I get is Ri bar cross Vi bar. Now, we can clearly see from the diagrams that the Ri bars and the Vi bars are perpendicular to each other. So I can clearly write it as Mi Ri into Vi, the magnitude of Li. But if I want the direction, now how to decide the direction? Magnitude is easy, and we have got it. Li is equal to Mi Ri Vi. How do we get the direction? So for that, we use the cross product rule. And we can see that all the Ri's and Vi's, they are all in the horizontal plane. So let's say the Ri is like this and the Vi is like this, and they all are in horizontal plane. And we have to find out the direction of Ri bar cross Vi bar. So if we observe from the top, then Ri bar cross Vi bar the direction can be found out by rotating Ri bar towards Vi bar. So when we rotate Ri bar towards Vi bar and we observe from the top, if we place our eye over here, we can see that the rotation from Ri to Vi is an anti-clockwise rotation. And whenever the rotation of the vectors from first vector to the second vector is anti-clockwise, the cross product is always towards us. the cross product is always towards us. If it is an anti-clockwise rotation, the cross product is always towards us. So by using this basic rule of cross product, we can easily see that for all the particles for which the r's and the v's are in the horizontal plane, the Li, which is found out by taking a cross product of r's and v's, is going to be vertically upwards, which is nothing but in the direction of omega. In the direction of omega. So all Li bars will be vertically upwards. Will be vertically upwards. All Li bars will be vertically upwards. Now, since all the directions of all the Li's are same, we can easily add them like the scalars. And when we add the angular momentums for each and every particle, we get nothing but the angular momentum of the body. So angular momentum of the whole body vector is nothing but summation of all Li bars, where I goes from 1 to n. And since they all have same direction, we can easily add them like vectors. So the magnitude of angular momentum of the body is going to be nothing but L1 plus L2 plus L3, so on up to Ln. And the angular momentum of the body will be nothing but, in place of Li, I can write down Mi Ri Vi plus, L1, I can write down M1 R1 V1 plus M2 R2 V2 plus M3 R3 V3, and the addition continues so on up to Mn Rn Vn. And we could only do this, the scalar addition. The scalar addition was only possible. Scalar addition only possible since all Li's, are in same direction. Same direction. Since all Li are in same direction. So this is the last equation that we had, that is the angular momentum of the body is m1r1 v1 plus m2r2 v2, so on up to mnrn vn. Now we know that v is equal to r omega. So in place of all the v's, we can substitute r omega. So I can write down m1 r1, and in place of v1, I can write down r1 omega. In place of v2, I can write down r2 omega. In place of v3, I can write down r3 omega, and so on up to, in the place of vn, I can write down rn into omega. Now if we add all this, I guess the terms that we are getting, we can take common omega. So we have m1 r1 square plus m2 r2 square plus m3 r3 square, so on up to mn rn square, and we have commoned out omega. Now if you concentrate at the term which is bracketed inside the bracket, it is nothing but summation of mi ri square, and that is nothing but the definition of moment of inertia. So the angular momentum for the rigid rotating body can be written as I omega. Now, if you want to give a vector notation, then L bar can be written as I into omega bar. So the direction of angular momentum will be similar to that of angular velocity. If the angular velocity is upwards axially, angular momentum will also be upwards axially. And if the angular velocity is downwards axially, the angular momentum will also be downwards axially. So this is the formula that we wanted to derive, which is nothing but L bar is equal to I into omega bar. And this is the angular momentum for a rigid rotating body. So let's write down the final statement. Therefore, angular momentum for a rigid rotating body, is given by L is equal to I omega. L is equal to I omega, where I is nothing but moment of inertia about the same axis of rotation about which we are finding angular momentum, and omega is nothing but angular velocity. Okay. So as we have derived the formula for angular momentum, now it's time to compare the formula of angular momentum with linear momentum. So we had formula for angular momentum which we derived, and that was L is equal to I omega. Linear momentum, we all know, it is mass into velocity. Correct? Now, an important formula when we are going to use this L and P is nothing but the formula for kinetic energy. In linear motion, the kinetic energy was half m v square, which is nothing but, which is also written as p square by 2l. Now, we have also seen the formula for rotational kinetic energy. Half remains half. In place of mass, we have moment of inertia, and in place of velocity, we have angular velocity. So half I omega square. But if we compare it with this formula, then the kinetic energy rotational, we should be able to write it as follows also. In place of momentum, I can take the square of angular momentum divided by twice, and in place of moment mass, I can take moment of inertia. So the formula for rotational kinetic energy can also be written as L square upon 2I. L square upon 2I. Okay. So let's solve a question based on the formula for rotational kinetic energy in terms of angular momentum that we just saw. Now in the question it is mentioned that a rigid body rotates with angular momentum L. If its kinetic energy is halved, the angular momentum becomes. So obviously they are talking about rotational kinetic energy over here. Now let's solve the question. So we know that the rotational kinetic energy can be written as L square over 2I. Now, what they are doing is the new rotational kinetic energy, let us call it KER dash, it is halved. So it is KER by 2. And that KER dash can be written as L dash square upon 2I. So if we use this equation 1 and 2, and if we equate them, we can easily see that L dash square upon 2I is equal to half. Kinetic energy rotational initial is L square by 2I. 2I and 2I gets cancelled, and we get L dash square is L square by 2. And from this, we can easily find out that L dash is nothing but L by root 2. So the correct option is D. So thus, in today's lecture, we have seen the angular momentum definition for a point particle. We have derived the formula for angular momentum of a rigid rotating body, and the formula that we got was L is equal to I omega. And then we also saw the formula for rotational kinetic energy in terms of angular momentum, which is nothing but kinetic energy rotational is L square upon 2I, similar to kinetic energy linear, which is nothing but P square by 2M. So that is all for today's lecture. Thank you very much.